This question is about atomic structure. It asks us to write the full electron configuration, that's starting with 1s, for each of the following species. So the first thing we need to remember is our order of filling. Our order of filling we'll go 1s, then 2s, then 2p, into the third shell, 3s and 3p. Then we remember that we fill the 4s before we fill the 3d, and then we go back and we fill the 4p. So this is our order of filling. We need to remember that an S subshell can hold 2, a P6 and a D10 electrons. You can bear all that in mind. And then we're asked to do the electron configuration of a Cl- ion. So the first thing that we should do is go to our periodic table and locate chlorine. So if we go and have a look at our periodic table here, and we find chlorine, here it is, it's atomic number 17. So we would then go back to our question, remind ourselves that chlorine is 17, so it has 17 protons, but a chloride ion would have 18, one more electron than a chlorine atom. To be negatively charged, 1 minus, it would need one more electron. So we've got to put 18 electrons in. So we start with 1s2, and we work our way along, 2s2, 2p6, 3s2. If we add that up so far, we've got to 12, so we need another 6, which is all of the 3p. Then we're asked to repeat the process for Fe2+. Now, when we find Fe2+ on our periodic table, we can see that it's in the transition metals here. Yeah, so we need to be careful because with transition metals, the ions you can't just fill from 0, because if you do that you won't end up with the right electron configuration, because when you lose electrons from a transition metal you lose them from the 4s first rather than from the 3d first. So you can't just do Fe as if it was the same electron configuration as the ion with 2 less electrons. So remember when we looked it up, it was number 26. Okay, so it has 26 protons. To be 2+, it must have only 24 electrons. So what I mean by my previous statement is, what I can't do is just do the electron configuration of chromium with 24 electrons and hope it will be right. That's not going to be right. So what I suggest you do with a transition metal ion is you actually write the full electron configuration, maybe in pencil towards the end, of Fe. So you start with Fe and you fill up for 26 electrons. So if I do that, I'm going to get here to 18, and then I'm going to fill 4s2, but notice how I've left a gap, and that is to help me with the removing electrons, because I'm going to group all the 3's together, and Fe would be 3d6. Okay, because that would be 26 electrons, 2, 4, 10, 12, 18, and then another 8, 26. Now we only want 24 electrons, so now I'm going to take my rubber, and I'm going to rub out the last 2, and notice how what I'm rubbing out is the 4s and not 2 of the 3d. So I end up with an electron configuration that ends 3d6. Our next question says, write an equation including state symbols that represents the third ionization of manganese. So again, be careful, read carefully. Manganese, if we look on the periodic table, is here, Mn, manganese. So we're going Mn. The third ionization energy is removing the third electron, so it would already be 2+. And we're going to make it 3+, the third ionization energy, by removing a mole of electrons. And the state symbols are, the definition says, in the gaseous state. Now our next question is about first ionization energy, and we're comparing magnesium and aluminium. So if we go back to our periodic table, magnesium's here and aluminium's here. They're in the same row of the periodic table. What you need to do is think about their electron configuration, or think about the shape of the graph for first ionization energy across a row. So magnesium is 1s2, 2s2, 2p6, 3s2, and aluminium is 1s2, 2s2, 2p6, 3s2, 3p1. You can see there what the difference is going to be about. Or if you remember the shape of the graph for first ionization energy across a period, it goes 2, drop a bit, 3, drop a bit, 3. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon for period 3. And you can notice that aluminium has dipped a bit. And if we look at the electron configuration, we can explain why. It's to do with this change of subshell. So which has the lower first ionization energy? Then we're going to say aluminium has the lower. Aluminium is one of those little exceptions. It's a dip. So aluminium has the lower. Okay, because the outer electron, the one that we're trying to remove, is in a new 3p subshell. So we're in a new subshell, and that subshell is higher in energy. Yeah, so we're sort of talking about slightly further from the nucleus, higher in energy than 3s. So less energy is needed to remove the electron. Yeah, there's a weaker nuclear attraction. Our question continues over the page. We're moving now. Notice we're changing elements to a sample of nickel. So nickel being Ni. And we're going to see it's got, the spectrum produced 3 peaks. So there are 3 isotopes of nickel. And we've got their abundances. It says give the symbol, so that would be the Ni part, including the mass number, that would be in the top left, of the ion. That means we need a charge that would reach the detector first. Now that's the bit of the question that relies on your understanding of time of flight, which is that the lightest ions travel the fastest. So we're going symbol, nickel, mass number, lightest, 58, and all samples in time of flight mass spectrometer by electron impact lose an electron to become a 1+. And then it says calculate the relative atomic mass, remembering that relative atomic mass is the sum of the masses times by the abundances. So the sum of the masses times by the abundances divided by the total abundance. Now, because these have been given as percentages, we know that that will be 100%. We type all that in our calculator. So this is going to give us 1. We do have to give our answer to 1 decimal place, so it might be worth going underneath the line and writing 1 dp. If you type all that in your calculator and round it up to 1 decimal place, you're going to get 58.9. Must be to 1 decimal place. Okay. So you want to type all that in your calculator and round it to 1 decimal place. If you had typed all that in your calculator did give you 58.879, and you did need to round it up to 58.9.